So guys, welcome back. We have one more topic to cover in the context of fast retransmission, and that's called redundant retransmissions. So we observed in the previous lecture that duplicate ACK enabled TCP to fast retransmit the lost segments, right? And this was a great optimization. The TCP do not have to rely on the expiration of retransmission timer in order to retransmit the lost segment. The reception of 3 duplicate ACK is an indication to TCP sender that segment has been lost or it's been received out of order on the TCP recipient. But this optimization comes with a cost. I have intentionally not shown the penalty paid by TCP to implement fast retransmission through duplicate ACK in the previous example. And I have not intentionally shown the penalty in order to simplify the example. So now let us discuss the disadvantage of fast retransmit through duplicate ACK, and that disadvantage is nothing but it is redundant retransmission by TCP sender. So now let us understand this disadvantage of duplicate ACK in detail. So you can see in this diagram, we have TCP sender and we have TCP receiver. And let us assume that the size of each segment is 100 bytes, right? So let us assume that the byte number from 1 to 100 has already been received by TCP receiver, and TCP sender is now transmitting the following 4 segments to the TCP receiver. Now out of these 4 segments, let us suppose that the segment with sequence number 201 has been lost. So it means that the TCP receiver will process segments with sequence number 101, 301 and 401. And therefore it will create a hole in the receiving buffer of TCP receiver, right? So you can see there is a hole. The bytes with sequence number 201 up to 300 are missing, right? So as a result, this segment, this particular segment and this segment will trigger ACK, each ACK with acknowledgement number 201, right? We already know TCP do not like holes in its TCP receiver, and TCP receiver always try to fill the holes first. So in order to fill this hole, the TCP receiver will issue the acknowledgement with acknowledgement number 201 in response to every data segment it receives from TCP sender. Now you can see that at this point of time, the TCP sender has received 3 duplicate ACK with acknowledgement number 201. Now let us come to the case 2. Here we assume that the segment number with sequence number 201 and 301 have been lost in the network. So as a result, it will create 2 holes in the receiving buffer of TCP receiver, right? Bytes with sequence number from 201 up to 400 are missing from the receiving buffer of TCP receiver. So as a result, the data segment 101, 401, and let us assume there is one more data segment, say 501, which is coming from the TCP sender. So these 3 segments will trigger TCP receiver to issue ACK with acknowledgement number 201. And therefore, as a result, at this point of time, the TCP sender has received 3 duplicate ACK with acknowledgement number 201. So you can see from TCP sender perspective in case 1 and case 2, the TCP sender cannot distinguish whether it's only the segment with sequence number 201 is lost or its segment with sequence number 201 and segment with sequence number 301 is lost. The TCP sender has no information about this. The TCP sender has no information about how many segments has been lost in the network. The reception of ACK 201 only tells the TCP sender that TCP receiver has successfully received bytes from sequence number 0 to 200 only. It doesn't say what is the status of bytes beyond sequence number 202 up to onwards. Of course, because TCP sender is receiving ACK 201, TCP sender can certainly say that the byte with sequence number 201 has not been delivered to TCP receiver. But TCP sender do not know the status of bytes with sequence number from 202 and onwards, right? You can see in case 1 and in case 2, in both the scenarios, TCP sender is receiving similar response from the TCP receiver, irrespective of the fact that in case 1, it was segment 201 which was lost, whereas in case 2, it was segment with sequence number 201 and 301 which were lost. So going forward, both the cases are identical to the TCP sender, right? ACK201 tells TCP sender that receiver has received bytes up to sequence number 200 only. Beyond that, TCP sender do not know anything about rest of the bytes, that is from 202 up to 500. Whereas TCP sender knows that byte number 201 is definitely not received by TCP receiver because it is receiving an ACK with acknowledgement number 201. So what do you think? What TCP sender should do in this case? TCP sender now do not know whether it has to retransmit the segment number 201 only, or it has to retransmit the segment number 201 as well as segment number 301. TCP sender has no information about any bytes beyond sequence number 202. So as a result, TCP sender uses a brute force method and it retransmits all the bytes which is beyond the sequence number 201 and onwards. Similarly, in the second scenario, the TCP sender will do the same thing. It will retransmit all the segments with sequence number 201 and onwards. So you can see that in the second scenario, the TCP sender also has to send the data segment with sequence number 501. So you can see that in the case 1, segment number 301 and 401 are unnecessarily retransmitted. So this segment and this segment has been unnecessarily retransmitted by TCP sender, irrespective of the fact that the segment which was lost was only segment with sequence number 201. Segments with sequence number 301 and 401 were successfully received by TCP receiver. But still TCP sender has to retransmit these two segments again because ACK201 only tells the TCP sender that bytes up to sequence number 200 has been successfully received by TCP receiver, and what is the status of bytes beyond sequence number 202 is not known to TCP sender. So TCP sender has to adopt to a brute force method and has to retransmit all the bytes again beyond and including sequence number 201 and onwards. The same goes in the case 2 as well. So in case 2, segment number 401 plus segment number 501 has been unnecessarily retransmitted by TCP sender, despite the fact that data segments with sequence number 401 and 501 were successfully received by TCP receiver in their first attempt itself. So now you see the problem here. The duplicate ACK helps TCP sender to implement fast retransmission, and TCP sender can retransmit the lost segment 201 as soon as it receives 3 duplicate ACKs. But at the same time, TCP sender has to retransmit all the segments which were already transmitted and received by TCP receiver in the first attempt. So in general, duplicate ACK triggers retransmission of lost segments instantly, right? And this was the advantage of duplicate ACK. But at the same time, duplicate ACK also triggers retransmission of already transmitted unlost segments. And this is the disadvantage, right? So the solution to this problem is again selective acknowledgement. So shortly we will going to discuss the concept of selective acknowledgement in detail, and we will discuss that how selective acknowledgement solves the problem of multiple holes in the receiving buffer of recipient TCP, as well as how it solves the problem of redundant retransmissions by duplicate ACK.